Okay, so hello everyone. In this video, I wanted to show you how you can compute the Thevenin and the Norton equivalent of any circuit. Um, in this case, what is the Thevenin equivalent? The Thevenin equivalent essentially is simplifying the circuit with a voltage source, okay, a voltage source that we call the Thevenin voltage in series with a resistance or an impedance. Okay, so we want to represent this circuit that we have right here with only a voltage source and an impedance. Okay, that is the Thevenin equivalent. And the Norton equivalent is essentially placing a current source, okay, in parallel with the impedance. Okay, this is a current source that we'll name the Norton current. Okay, and these two equivalent circuits basically can be are related. No, for example, the Thevenin impedance, okay, is equal to the Norton impedance. Okay, and you can compute the Norton current by using the voltage, the Thevenin voltage divided by the Thevenin impedance. Okay, that this is also equal to the Thevenin voltage divided by the Norton impedance. Okay, and also you can compute the Thevenin voltage. Okay, if you know the Norton current times the Norton impedance. Okay. So the idea is, okay, we want to simplify this circuit by expressing this circuit using the Thevenin or the Norton equivalents that are basically these two circuits that we have right here. And also I wanted to mention that this equivalent circuit depends from which point of the circuit you want to compute that equivalent circuit. For example, here in this problem, we need to compute the Thevenin voltage according to terminals A and B. Okay, but also you can write the terminals in this position, for example. Okay, so if you compute the Thevenin equivalent or the Norton equivalent according to these terminals that are in the inductor, well, you will obtain a different result. Okay, so the equivalent circuit depends mainly from which position you are computing the Thevenin equivalent or the Norton equivalent. Okay, so the approach that we'll be using here in this class is to first compute the Thevenin equivalent according to the terminals that are given by the problem. And based on that, we can compute the Norton equivalent. Okay, so that is the way in which we can solve this type of problems. Okay, well, so the first thing that we need to do is to compute the Thevenin voltage according to the terminals A and B. Okay, so the first step is to compute the voltage A and B, that for this purpose is equal to the Thevenin voltage. Okay, but we need to be very careful in this type of circuit because you need to consider this link. Well, here I am placing the current I1, okay, that is flowing from the negative to the positive terminal. And this current I1 is flowing through the inductor, and then you need to be very careful in this branch because you can notice that in this region, there is no current flow, okay? And the reason for that is that we have here an open circuit between terminals A and B, okay? Since we have here an open circuit, there is no current flow in this direction, okay, through the branch of the 10 ohm resistor, okay? So in this case, the current I1 will be will go to the capacitor, okay? There will be no split of the current value of I1 between these two branches because all of the current, since here we have an open circuit, will go only through the capacitor, okay? But the reason of that is that through this direction, Okay, there is no current flow because here we have an open circuit. Okay, remember that an open circuit implies that the resistance is infinite. Okay, so that is why through this direction there is no current flow. In other words, there is no voltage drop, okay, in this element, okay? Since we have zero current, there is no voltage drop. So based on that, we can say that the voltage between terminals A and B should be equal to the voltage of the capacitor, okay? The capacitor in this part has the following impedance, okay? But that is the reason for that, okay? Since in this section we don't have a current flow, okay, there is no voltage drop in this element, and based on that, we can say that the voltage between terminals A and B is equal to the voltage of the capacitor. Okay. Now, well, what we can do in order to compute the voltage of the capacitor? Well, the first step is that we can apply the Kirchhoff voltage law. And if you apply the Kirchhoff voltage law in this loop, well, we need to follow the direction of the current, okay? So here you can see that I1 is flowing from the negative to the positive terminal. So we place a negative sign that is 50 with an angle of 30 degrees volts plus I1 times the impedance on the inductor, that is J times 20 ohms, plus the voltage of the capacitor, that is I1 times the impedance of the capacitor, that is minus J 10 ohms, and this is equal to 0. So based on that, you can compute the value of I1, that is equal to 5, with an angle of minus 60 degrees amperes. Okay? Now, you can observe here that the voltage of the capacitor, okay, is equal to the current I1 times the impedance of the element, that is minus J 10 ohms. Okay? So we can say that the Thevenin voltage, that is equal to the voltage in terminals A and B, that is equal to the voltage of the capacitor, is equal to this expression of I1 times impedance of the capacitor. So we can substitute I1 and this impedance, and we will have 5 with an angle of minus 60 degrees amperes times impedance. Okay, and this is equal to 15 with an angle of minus 150 degrees volts. Okay, so this is the Thevenin voltage. Now, now we can compute the equivalent impedance. So to compute the equivalent impedance of the circuit, what you can do is to first turn off the sources of the circuit. So here we have this current, this voltage source, okay? And we need to turn off that element. So in order to represent that, we can, instead of writing or drawing the voltage source, we can write a cable, okay? And the reason of using a cable is that in a cable there is no voltage drop, okay? The resistance is so small that there is no voltage drop, okay? So we rewrite the circuit, but instead of writing the value of the voltage, okay, we write a line only, a cable. Then we have here the value of the inductor, that is J times 20 ohms. Okay, here we have the value of the capacitor. Okay, that is minus J 10 ohms. And here we have the value of the resistance. Okay, that is 10 ohms. And we have here A and B. So what else we can do? Well, you can observe in this part that these two elements are in parallel, okay? Because they are sharing two connections, no? This node and this node. So this capacitor and this inductor are in parallel. So we can simplify the circuit as follows. The parallel between the impedance of the capacitor and the impedance of the inductor is equal to 1 over minus j 10 ohms plus 1 over j 20 ohms. And this is equal to um, minus 20 j ohms. Okay, so we can again rewrite the circuit as follows. Okay, we have minus 20 j ohms, and here we have the 10 ohm resistor, and we have here the terminals A and B. And you can observe here that these two elements, or the equivalent impedance between these two elements, is in series with the 10 ohm resistor. So this is equal to the equivalent impedance as minus 20 j ohms plus 10 ohms. Okay, if we simplify these two elements. So this is the equivalent Thevenin impedance, and remember that this is equal to the Norton impedance. Okay, so we can also compute the Norton current that is equal to the Thevenin voltage divided by the Thevenin impedance. Okay, so the Thevenin voltage is equal to 50, okay, with an angle of minus 150 degrees, and these are volts, and this is divided by the impedance, that is 10 ohms minus 20 j ohms, and this is equal to um this is equal to 2.236 with an angle of minus 106.56 50 degrees amperes. Okay, so this is the Norton impedance. Okay, so you can express by using those values, the Thevenin voltage, the impedance, and also the current, the Norton current, to express the circuit via Thevenin equivalent or Norton equivalent. Okay, so this is one of the examples that I wanted to make. I think that we can make another example, and then you make another one by yourselves. So here we have the current. Okay, we have a current source that has the following value, that is 4 amperes with an angle of 0 degrees. I will rewrite this again. So here we have the current source that has a value 4 ohms with an angle of 0 degrees amperes. Then we have here the 8 ohm resistor. Here we have the capacitor of minus J 5 ohms. Here we have the inductor. Okay, and the inductor has impedance of J 10 ohms. And here we have the terminals A and B. And okay, so remember, the first step is to compute the voltage according to the terminals that we have. Here we have the terminals A and B, that is equal to the Thevenin voltage. Okay, you can notice that the voltage between these two terminals is essentially the same voltage of this element of the inductor. Okay, and this is the Thevenin voltage. So we need to find a way in which we can compute this voltage of this inductor. So to do that, what we can do is to apply mesh analysis. For example, okay, I will label this current as I1, and this current will be I2. Okay, and okay, you can observe here based on this mesh analysis that for mesh number 1, okay, I1 is equal to 4 with an angle of 0 degrees amperes. Okay, this is for mesh number 1. And for mesh number two, what we can do? Okay, so the idea is to apply mesh analysis in this loop. So the voltage drop for the 4 ohm resistor, I will assume that this is positive, and the current that is flowing through this 8 ohm resistor is basically the difference in currents between I2 and I1. Okay, I2 minus I1 plus the voltage drop in the capacitor that is minus J 5 ohms. Okay, this is the value of the impedance. And the current that is flowing through the capacitor is I2. Okay, and now, well, you can observe here that in this loop, the voltage drop in the inductor is equal to I2 times the value of the impedance of the inductor. And well, we can close the loop in this section, and this is equal to 0. Okay, so this is for this mesh. And what else? Well, also, we can say that the voltage of this inductor is equal to the current I2 times the value of the impedance of that inductor. Okay, so with this expression, we can compute the voltage between terminals A and B. So you can substitute, well, you can input these two equations in your Texas, and you will obtain a value of I2 that is equal to 3.3919 with an angle of minus 32.005 degrees amperes. Okay, and that's it. No, this is the value. Now, with this value, you can substitute this value into this expression, that is the voltage of the inductor, that is equal to the voltage between terminals A and B, that is equal to the Thevenin voltage, and this is equal to, well, we need to substitute I2 into this expression, and you will obtain the following result, that is 33.9199 with an angle of 57.9946 degrees, and these are volts. Okay, so this is the voltage, no, that we have. And what else? Okay, so this is the Thevenin voltage, and now we need to compute the Thevenin impedance. Okay, so remember that to compute the Thevenin impedance, we need to turn off all of the sources in the circuit. So here we have this current source. So to turn off that current source, what you need to do is to redraw the circuit by assuming that this thing is off, and you can represent that. Since here we have a current source, we can represent that with an open circuit, okay? And the reason for that is that we are using an open circuit to represent that this source is off, is because in an open circuit there is no current flow, okay? So that is the way in which we can say that this current source is off, okay? So we can rewrite the circuit. Here we have the 8 ohm resistor. Now we have here the impedance of the capacitor, and here we have the impedance of the inductor. Okay, that is J10 ohms. Here we have the terminals A and B. Okay, so we need to simplify this circuit according to terminals A and B. So you can observe here that these two elements are in series. Okay, here we can, in fact, we can erase this part of the circuit because there is no contribution, okay, in this part when we switch off the source, okay? So we can rewrite the circuit in this way, and you can observe that these two elements, the 8 ohm resistor and the impedance of the capacitor, are in series. So we can simplify the circuit as follows. Here we have the impedance of the equivalent impedance between these two elements, that is 8 ohms minus J 5 ohms. And this is in parallel, okay, with the impedance of the inductor, okay? So the parallel between this impedance and the inductor is equal to 1 over 1 over 8 ohms minus 5 minus 5 j ohms plus 1 over j 10 ohms. And this is equal to, just a moment. Well, you can express this in polar form and you will obtain 10 with an angle of 25.98, 92 degrees ohms. Okay, so I am expressing this impedance in polar form. Okay, you can use your calculator to compute that. And um, well, this is in fact this simplified circuit is the Thevenin impedance. Okay, and what else we can do? Well, we can compute the Norton current that is equal to the Thevenin voltage divided by the Thevenin impedance, and this is equal to, well, we got a value for the Thevenin voltage of 33.9119 with an angle of 57.9946 degrees volts, and this is divided by 10 with an angle of 25, 19, 98, 92 degrees ohms, and this is equal to 3.3919 with an angle of 32.4453 degrees, and these are amperes. Okay, so this is the way in which you can tackle this type of problems, and it is not too difficult. And well, I think that's all for this video. I hope you like it and see you later.